Okay, well, today we're going to do a couple of things today because what I've been doing is giving you as gentle an introduction to supersymmetry as I can. So we've boiled it down so much that, in fact, the models that I was talking about really have no direct application to things. Well, that's not quite right, but almost no direct application to interesting things. So today what I wanted to do was a couple of things. First of all, I want to sort of kill off the kind of gentle introduction. By the way, I don't know if anyone actually worked out those constants. They turned out to be 1, at least according to my calculations. But what I'd like to do today is we're going to switch gears because I would like to take you to where we are in string theory, because these tools turn out to be the useful sorts of things actually for superstrings. And I have a dual goal today. Having understood the principle of supersymmetry, and I now think of you as having understood it, I want to take this experience and put it in two places. Strings is one place, and M theory, we're going to talk about what these things mean. But the other place where we want this experience is in the context of the standard model as Professor Z had given you before. So these are sort of two divergent goals, but having learned the principles of supersymmetry, we now can perhaps begin to think about applying those goals. So that's what I'd like to do today. So let me start by summarizing what we've learned so far. What does SUSY mean? Well, it means, first of all, that there is some kind of a supercharge, and that once we know that this supercharge exists, it must satisfy a graded, what's called a graded commutator algebra, which we can write as gamma mu alpha beta times p, where p is the translation operator. That's what we learned in 1 dimensions from our gentle introduction. And whenever this property is satisfied, then that's the end of the game. Now, there's a couple of generalizations I should say. First of all, if you have a superspace where Q is complex, then this definition isn't quite sufficient, because if this were true, if Q is complex, it would imply that P is complex according to this definition. And of course, the translation is a Hermitian operator for us. So if Q is complex, so Q alpha not equal to Q alpha star, then what we really want is to replace this identity by the following. We want Q alpha times Q beta. Think of these as matrix operators, so it's better to call them Hermitian as opposed to conjugate. So if the supercharge is not equal to its Hermitian conjugate, then in fact the relationship we want satisfied looks like we replace the second one by Q Hermitian conjugate, and then that ensures the hermiticity of the translation operator. So this is a slightly more general statement of supersymmetry. So whenever the supercharge is complex, this is the equation you want satisfied, not the one on top. This is only for real. Or, I'm sorry, Hermitian. Okay. Now, these things, the gammas, showed up 2 lectures ago, and we certainly talked about them a little bit yesterday. And let me, at this point, just take a poll. How many of you have actually talked about the relativistic Dirac equation? A few of you, but not the majority. So let me just take 5 minutes or so to try to get you familiar with the Dirac gamma matrices. And because they're really, although they're very important, they're really ultimately not very difficult. The Dirac gamma matrices, as I said yesterday, they have 2 kinds of indices attached to them. These indices here we call spinor, and typically they take some values from 1, and it turns out that these have to be even dimensional matrices, so there's never actually a case where they're odd dimensional. So actually, if we're being careful, we should really say that this goes up to 1 from 1 up to 2 to some integer that I'll call, let's call it f. F is just some integer. On the other hand, the label mu, well, mu can actually do lots of interesting things. If you're talking about the context of special relativity, which is where, in fact, we physicists first met the Dirac gamma matrices, then the label mu goes from 1, and if you're doing just special relativity, then it goes up to 4, because there's only time, the x direction, the y direction, the z direction, then it stops. Now, we can, in fact, generalize this mathematically. And in fact, in the context of string theory, which now you've heard about all these weird 10 and 26-dimensional spaces, for those spaces, if you want to talk about spinors, you have to allow this index to go all the way up to d minus 1. So you have to go for, so this is for 4-dimensional physics, like the standard model. So let's put standard model here. So in the standard model, you would want matrices with this is true. But in string theory, or M theory, or superstrings, all these nice, strange names that people use, you want this index to go from 0 to d minus 1, wherever d is the appropriate dimension someone tells you to work in. If it's 10 dimensions, then this goes from 0 to 9. If it's 26-dimensional bosonic string, then this index must go from 0 to 25. Now, so those are spinor indices. And this index that has this range here, we call the vector index. And as someone pointed out yesterday, this is the index that the Lorentz transformation, that the Lorentz d vector would carry. So it's the vector index. And so this thing really has 3 different indices of 2 different types. Now let me actually, before your very eyes, construct some of these things so that you can become convinced that they actually exist and they're just not abstract objects. In order to do that, I'm going to treat 2 cases. I'm going to treat the case of d equals to 2 because it's very simple to figure out how this works for 2 dimensions. And then we're going to also treat the case of d equal 4 because that's apparently the dimension that we who are experimentally attached to our universe, we believe 4 is somehow the place we ought to look. So those are the cases I'm going to look at especially. So let me start with the case of d equal 2. So in d equals 2, this, because of the way the indices work, we require a gamma 0 that has some alpha and beta indices and a gamma 1. And that's all, because this range always goes from 0 to d minus 1 on this index. And the defining property of gamma matrices, as we wrote yesterday, is that they have to satisfy the following equation. Gamma mu alpha beta times gamma nu beta delta, and then you write it in reverse order on the interchange of the vector indices, alpha beta mu beta delta. And now the other side really depends on your convention somewhat. I'm going to pick a set of conventions where the other side looks like 2 times eta mu nu, and then times the identity matrix. And the identity matrix actually carries the alpha and the delta indices. If you look at many textbooks on the definition of gamma matrices, you don't see so many indices, because what one finds, this is supposed to be the same thing as if in most textbooks this would be written as gamma mu, gamma nu, plus gamma nu, gamma mu is equal to 2 times eta mu nu. If you look in lots of textbooks, that's what you'll find written. But when they're doing that, they're suppressing the rows and column labels that these alphas and betas label. They're the labels for the rows and columns of the matrix. So if you're being very explicit about the form of the gamma matrices, you write this. But implicitly saying, well, I know those indices are there, but I don't want to bother to write them, you write this equation. So these things really are the same. And now, I promised you I was going to actually find some of these things in the case of d equals to 2. Well, for d equals 2, eta mu nu is itself a 2 by 2 quantity. It only has two non-zero entries, eta 0, 0, and eta 1, 1. I can pick my conventions so that eta 0, 0 is equal to the number 1. And then if that's the case, then I must pick eta 1, 1 to be equal to minus 1. Eta 0, 1 and eta 1, 0 are identically 0 because the off-diagonal terms are always vanishing. And therefore, this is a set of conventions. Okay, so now I've got my metric fixed. I'm trying to find some solutions to that equation. Let me simply give you a set of solutions. Let me pick gamma 0 to be alpha beta to be equal to the second Pauli matrix. And the alpha and beta tell me which row and column entry I'm in the second Pauli matrix. And I can pick gamma 1 alpha beta to be equal to, let's pick it equal to I times gamma 1 alpha beta. Now, did I solve the problem? How do you check to see if I solved the problem? Well, if this is a solution, it's supposed to satisfy that. So does it? Well, first of all, that equation above that I just, if you ask, what does it mean if I pick gamma 0, alpha, beta, gamma 0, beta, delta, plus gamma 0, alpha, beta, times gamma 0, beta, delta. That's 2 times eta 0, 0 times the identity, alpha and delta. And now, according to our conventions, eta 0, 0 is the number plus 1. And so the question is, if I take this matrix and multiply it by itself, do I get plus 1? The answer is yes. You rapidly conclude that the answer is yes because the second Pauli squares the identity. So that works. And now, what if I square this matrix? Well, gamma 1 times, the thing I'm calling gamma 1 is actually I times sigma 1. Sigma 1 squares the identity. The factors of I produce the minus 1 that's necessary to go with this. And now what about the off-diagonal terms where I pick a 1 and a 2? Well, gamma 0. And now I'm going to suppress indices like your textbook because, as you can see, it's a real pain to write them. So gamma 1, gamma 0. I'm sorry. What is that equal to? Well, plugging in these definitions, we just get sigma 2 times sigma 1 plus sigma 1 times sigma 2, a factor of I, and sure enough, that's 0. So we got our solution. In 4 dimensions, we can also write solutions. So here we'll do d equal 4 really quickly. As I said, this is just a lightning fast review. The case of d equals to 4, I can pick gamma 0 alpha beta to be itself, I can pick it to be, oh boy, I need some notation here. Let me pick it to be equal to 1, 1, 0, 0, zeros here, minus 1, 0, 0, and minus 1. The square of that matrix is identity. It's hopefully pretty easy to see. What about the other gammas? So for the other gammas, I can pick the following. I need 3 of them. And interestingly enough, there are exactly 3 Pauli matrices. So let me just start with gamma 1. I can write this as the first Pauli matrix on the diagonal. No, I'm sorry. I can write this as the first Pauli matrix in the off-diagonal, zeros. And if you square this, it'll be 1. And if you do 1, 2 plus 2, 1, you'll get 0. So we get all the gamma matrices. And while that's just the gamma 1, I do the same for gamma 3, or gamma 2, and gamma 3 by putting Pauli's off-diagonal. So it works. And if you want more dimensions, it becomes harder to find these things, but you can always do it. So the gamma matrices always exist. And the question is only to find the matrices to realize the algebra. Okay, so that's my lightning quick review of gamma matrices. Okay, now, we want to go back over and discuss, as I said, we want to discuss how do you actually realize this idea in a real-world theory? Something like this, we'll start with string theory. How do we realize it there? Well, let me show you, building on Dr. Becker's lecture. All the discussion of string theory that she started with began with an object that looks like this. It was a function of two variables, sigma and tau, and it had an index that lived in a d-dimensional space. Now, I want to introduce a kind of supersymmetry. Now, in our toy example that we discussed rather extensively yesterday, there was an x. And the way that you got supersymmetry was by introducing another variable psi, so you need a fermion to accompany this object. So if we're going to get some kind of realization of supersymmetry, we have to add in something else to the model. There's something else we can choose to be it's a spinner, just like yesterday we introduced a spinner. However, we're going to do something a little bit weird. This index here, which is a space-time label, a Lorentz vector index, we're going to demand that that index be carried by this object. That's a little bit weird because we said it's a spinner, but it carries a vector index. Well, things cannot be spinners and vectors. I'm sorry, something that is a spinner ought not carry a vector index. And so the way out of that is that you attach another index to this object that is truly a spinner index. And now we have a function of tau and sigma. And now what you really ought to ask me is, how big is this spinner index? Because over there I showed you two examples. This could be take on two values, or it could take on four values, or in fact it could take on any number of even values. In order to talk about the string, the idea is these two quantities here look like the coordinates of a manifold. And so the simplest spinners you can introduce are the spinners that are associated with these coordinates, not the spinners associated with these coordinates. And so we pick alpha to take on two values. Now we've got a spinner. Now it's a very strange object. It does carry a vector index, but it is a spinner with respect to the space where these things play the role of coordinates.
So is that vector index telling you which spinner you're looking at?
Well, whatever you think this label does for the x's, this label is doing the same for these spinners. But they're spinners, what we say is that they're spinners on the world sheet. Okay? Now, so what we're doing is we're taking Susie and we're adding it to string theory. So this is what we're making the transition from the bosonic string to what's called the Nevers-Schwarz-Ramon string. You have to add a fermion. That's the first step. If you don't add fermions, you never can get supersymmetry. So you're forced to put fermions. Now, once we add these fermions, then we have to start worrying about a couple of issues. The first issue is what are the supersymmetry transformations? Or, equivalently, for the case of the pure bosonic string, Dr. Becker showed you a Lagrangian from which you derive the Hamiltonian and the spectrum and everything. So let's attack the first problem, the problem of the Lagrangian first. The Lagrangian for the purely bosonic string, as you now have become all expert to know, takes the form of, you have to introduce let's see, this is going to be interesting. Let me introduce another label, call it A, and it will be taking on two values. In fact, it's going to take on the value, it's going to take on, I'm sorry, how do I say that? It is sort of, let me introduce a symbol, tau A, whose definition is A, if it takes on the first value, is the quantity tau, And if it takes on the second value, it's the quantity sigma. Okay. If I introduce such a notation, then this looks like a little two-dimensional Lorentz space. I can introduce an invariant here, invariant, and we've talked about invariance a lot in these lectures. Tau square minus sigma square. That's Lorentz invariant, but not for a four-dimensional world, but for an imaginary two-dimensional world. And so if we have this imaginary two-dimensional world, there's a two-dimensional metric. And that's the important thing I want to get at. And in fact, we talked about that metric explicitly over there, just in the abstract saying, let's look for some examples of solving the gamma matrices. So I'm going to go ahead and introduce that metric. So this implies an eta AB, whose values are minus 0, 0, and 1, just as I wrote over there. I didn't write it as a matrix over there, but it exists. Since I have two coordinates here, I can take their derivatives, just as you've seen before. So I'm going to use the symbol d by d tau A, and that's going to stand for the derivative with respect to this, or the derivative with respect to sigma. And we're going to need all of these pieces to actually write down the action. And then there's one more thing that you already know about. Namely, since this thing is a vector in d dimensions, there's also a d-dimensional Minkowski metric. So this eta mu nu, which is minus 1, dot, 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 I'm sorry, 0, dot, 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 0, dot, 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 and then it's plus 1 down the diagonals until you have saturated the dimension that you're in. Right? So these are things that we've all seen. Okay, now, I'm going to take all of these pieces and write down the bosonic string action. Sorry? Oh, yes, you could, but then the life simply gets more complicated. Actually, we do it. In fact, I do it quite often. It turns out that what you get then is what's called a nonlinear sigma model. And in fact, nonlinear sigma models are very useful objects for studying strings. But we're going to just keep life simple in this discussion by saying we're just going to fix eta to be the flat Minkowski metric as opposed to being some function. Okay? Yes? This one is only a 2 by 2 matrix. This one is a D by D matrix.
So is it possible to have written AB as a D by D matrix? We have defined it.
We have defined eta to be the Minkowski metric associated with that invariant. So it can have no more than 2 entries because there are only 2 coordinates there. So this is a strange thing about the string. In fact, this is getting us very much into the discussion of the string. You see, the string has 2 kinds of spaces that it worries about. There's the space of tau A. This is what's called the world sheet. So we can imagine a space. It's a little 2-dimensional space. It's the little surfaces that you draw pictures of when you draw string theory, typically. So there's the world sheet. And then there's another world in string theory. It's called the target space, the target manifold. And what are the coordinates of the target manifold? It's the string itself. The string has a vector that talks about this other space. So one way, again, a picture we often draw of the string is that it is a map. One way to think of the string is you take a 2-dimensional plane, tau and sigma. There's a picture of our 2-dimensional space. And now you need a multi-dimensional space. So I'll just draw 3 axes, but you need, for the bosonic string, you need 25 of these things. And what the string does is tell you how to map points in here to points over here. And it's done by precisely x mu of tau and sigma. And in fact, that's the typical meaning of what you say a function is. A function is a map from one set of numbers to another. It just turns out, in the string case, the way this map works is that it maps from the 2-dimensional space into the d-dimensional space. Yes?
B? Is it supposed to be +1, -1?
No. Let's see which. Thank you. Yes, because I'm using. Thank you, because I'm. Yes, thank you. And same thing here, because I'm using all minuses on my metric. Okay, so how do we write the action for the string knowing all of this geometry? You write down the most natural thing that there is. Well, what's the most natural thing that there is? Well, kinetic energies for bosons are quadratic in derivatives. The string, from the point of view of the two-dimensional space, looks like 25 bosons, 25 scalars, in fact. So you write down the only thing that you write for a scalar, namely del A x mu, del B x nu, because that looks like the kinetic energy for a scalar field. However, the Lagrangian itself has to be a scalar. We can accomplish that, and now, of course, we're really approaching Dr. Becker's lecture because now we've contracted away these two-dimensional indices, but this is still not a scalar. In order to get a scalar, we still need to also contract away the d-dimensional indices. So the string is a very complicated theory with two different spaces involved. Now, we're not quite finished yet, because if you actually followed Dr. Becker's lecture, you might have remembered a square root somewhere popping up. Where's that square root? Well, the way that we can deal with the square root turns out to be that you don't we can introduce a kind of gravitational field, a fictitious gravitational field in the two-dimensional space. Now, what that does for you is, if the two-dimensional space were purely flat, that's the appropriate way to contract the indices. But if there's a form of gravity on this two-dimensional world, then you have to introduce a two-dimensional gravitational metric. And now, of course, you got a problem because this is not two-dimensionally generally coordinate covariant. So now the additional step is you say, to make it coordinate covariant, I have to take the determinant of this metric, and now we have reached, and put a factor of 1/2 in for good measure, and you might want to put an integral and, appropriate normalization of 1/4 pi alpha prime or whatever your convention is. But at this stage, we have finally reached the form of the string. Very complicated structure, but nonetheless, there it is. Now, I've written this theory in terms of a metric. In terms of a two-dimensional metric. Now, it turns out that these objects are two-dimensional spinners, because that's how we introduced them. We said we wanted some kind of supersymmetry, and so I said, well, the simplest spinners are those that are associated with this manifold. So if this thing is a spinner, it turns out that this formulation of the string is not the most convenient way to take as a starting point. Because spinners have a very funny property. Namely, in order to have general relativity in the presence of spinners, you can't just introduce the metric. You have to introduce something known as the frames. How does that work? So, from 2D metric to 2D frames. Well, the basic idea here is that the set of functions, GAB, which are functions of sigma and tau, you simply assert, you say, I demand that this set of functions can be written in the following form. E, AI, eta ij times E, aj, where the E's are functions of sigma and tau. Now you might say, well, gee, and this eta, by the way, is our two-dimensional flat Minkowski matrix with just pluses and minus signs and zeros. So we say that the generally curved metric that you saw in the string lectures factorizes into three objects. And these things here are called frames. They actually have a lot of different names. We can also call them Zweibinds. And if there's anyone who actually speaks German in here, you'll immediately recognize why we might want to call this a Zweibein, because Y for two, and they're like little legs, and they are. Now, once you introduce the frames, we can go back and use that definition up here. Oh, I'm sorry. You guys let me get away with murder, right? Einstein says square root. It doesn't say G, it says square root G that goes there. Okay, so now once you take this as the starting point for the bosonic string, then if we're going to switch to this notion of frames, we have to consistently make that change a variable. Now, how does that actually work? Well, we can take L sub B, still 1/2. So so first of all, the instruction here is calculate the determinant of G. So let's do that calculation on this expression. So right here. Determinant, GAB, must be equal to the determinant of EAI, eta ij, times EBJ. But what is the property of determinants? If you take a determinant of products of matrices, it's equal to the product of the determinant of each matrix. So this thing is equal to the determinant of EAI times the determinant. Sorry. It's minus that. Sorry about that. There's always a minus here. In a moment, we'll see why that minus is very important. So it's the determinant of this, determinant of that, times the determinant of this last factor. That's taking the determinant of the product. And now you notice that, well, these two things are actually the same thing, because this matrix is the same as that matrix. This is a B. Even though the labels are different, when you take the determinant, the labels don't matter, because the determinant is a scalar. So the determinant of these two things is the same. So that's equal to the determinant of just one of these factors squared. And now we want to take the determinant of the flat Minkowski metric, but that's really easy because it's purely diagonal, and it's got one plus sign and one factor of minus one, one factor of plus one, and so therefore taking this determinant is just the number minus one. And now we see that minus the determinant of GAB must be equal to minus this, the square root of minus the determinant of GAB must be, well, this minus sign cancels that minus sign, and the square root cancels the factor of 2 here, and all we're left with is the determinant of EAI. So everybody okay with that? So now let's come over here. So at this stage, our bosonic Lagrangian looks like the following. It's of the form a half. That square root factor is no longer there if we write the theory in terms of E, and the minus sign is gone. So it's just determinant of EAI, and that's it. Now remember, there was this factor of, going back, there was our factor of GAB. Well, there's a little bit of a problem here. I introduced the frames to this equation. And remember, we keep the altitudes very important in the way this gets played. So G here has the indices down, whereas the G that occurs there has its indices up. They're not the same object. They are inverse to each other. Now, if this is true, if this statement is true here, then if you want a G with its indices up, which I guess I'll go over here, so we want a G with its indices up, if the G with its indices down factorized, then the G with its indices up also needs to factorize. And so therefore, there's an object, EA I, eta ij. Well, we know that the Minkowski metric has an inverse, so that part we're not confused about at all. And then the object ejb. There has to, if the matrix factorized and it has an inverse, then its inverse has to factorize. So there must be an object that's like of this nature. Notice, be very careful to notice the up and down height. The A is always down on this object, but the A is up over there. And that's how we, by the way, look for the inverse, by looking at the height of the index. This index A, which is what we call a curved index, if it's up, we know it's attached to the inverse frame field. If it's down, it's attached to the frame. In fact, this thing here is called the inverse frame. E-I-A, inverse frame. Okay, so we take the factorization, we just shove it into the equation. We get I'm sorry, in fact, let me write it in a slightly different way. Let me write it like this, because this is even more dramatically different, and we want to keep this difference very strongly in mind. So now it's going to be really easy to tell the inverse from the frame field. The frame field will have the A type of index down, but and it will be the first index, whereas for the inverse frame, the A type of index will be the second index on the quantity. So now, having introduced this, we take it, we plug it into the bosonic action. What happens when we do that? Well, the factor of eta ij is going to appear out front like that. We're also going to have a factor of EIA d by dA acting on x mu times EJB d by dB acting on x nu. And then our d-dimensional Minkowski metric rides along at the end of the calculation. Nothing changes in it. And so now we've got the same bosonic string, but just find in terms of this E variable, the frames. So here's a metric formulation. Where is it? This is the metric formulation of the bosonic string. This is the frame formulation of the bosonic string. Now that I did all this work to get to the frames, I can now introduce spinors, it turns out. Because you see, spinors, well, if I'm going to introduce spinors, as I talked about in my two-dimensional example right here, if I'm going to introduce spinors, then I need a set of gamma matrices that point in the direction of the Minkowski metric that's associated with them. The Minkowski metric here carries I and J indices. So the kinds of spinors I have to associate with this model have to be objects that look like this. They have to have I and J indices attached to them. So these are the spinor matrices associated with this model. So associated with EIA. Now, they still satisfy the same defining property, that you take the two of them, you add them together with opposite order, and it must be proportional to the two-dimensional metric times the two-dimensional identity. That still goes through. So all of this goes as that argument. But now, if you look at this theory, and if you have any training in relativity, this, of course, also looks familiar to you. Because this is nothing but a set of scalar fields coupled to a gravity, where the E thing plays the role of the gravity. This looks exactly like an imaginary whirl of two dimensions with scalar fields X coupled to the gravitational variable E. And if you go grab a textbook on general relativity, you'll find this exact expression there. So we take that expression down to two dimensions. Now, the next stage for us, as I said, is that we need to introduce these spinors. They have to have some kind of Lagrangian for them. Well, let's stop and think for a moment. If you start with a spinor, what kind of Lagrangian do you want? Answer, a Dirac-type Lagrangian, just like we did in our toy example yesterday. It has to be Lagrangian has to lead to equations of motion that are linear in derivatives for spinors. So it must be a Dirac type of Lagrangian. Well, that's pretty easy it's now pretty easy to figure out how such a Lagrangian would look. It has to have one factor of the spinor. It's got to have some derivatives acting on the spinor. So let me put those derivatives in like this. dA acting on a second factor, psi beta nu. Well, this thing is not a scalar. So we got a little bit of work to do to make it into a scalar. The first thing is, if you look very carefully, you'll see I did something really sneaky behind your back. I said the gammas have the indices associated with the metric. Is this the index that was associated with the metric type? The answer is no. Now that's an extremely important distinction because it means that you cannot write a gamma here with an A or a B index. The only kind of gammas we have ij indices. So such gammas exist, so let me put one there, ij beta delta. But then I've got to tie these two indices together. This is an I type of index. That's an A type of index. So what do I have an object that I can naturally tie these two indices together? The frame itself. The frame is something that carries one A type of index and one I type of index. So I can insert here AI, or rather EI, A. And now I've contracted those indices away appropriately. I still have a little bit of work to go. Notice I contracted away this beta index, so those indices aren't there. But there's still a free delta index. And there's a second spinner I have to put in because I'm looking for a direct type of Lagrangian. So let me introduce that second spinner back. It has an index, alpha. It's also got a space-time index, mu. And now we have to worry again about how do you form a scalar. Well, yesterday I introduced you to the notion of the spinor metric. The spinor metric is precisely an object that if you have two spinor indices, it gets rid of them. This object has two spinor indices. So if I insert the factor of the spinor metric, those are now gone. And now, the only other free sets of indices on here are the mu and the nu. But that was just like the bosonic string. And how did we get rid of those indices? By contraction with the d-dimensional metric. And so now we have a candidate Lagrangian. And Dirac Lagrangians always have factors of I here. If you go look in your textbook, you'll find it's all times I times psi d slash. So here's a factor of I. We have a candidate, but if you've done gravity, you know that if you see a factor like this for the scalar, that same factor has to be written in front of the spinor because it guarantees coordinate invariance. So we have to insert, in order for coordinate invariance, we have to put the I here, and then put another factor of determinant of EAI. So this is our candidate, ansatz, for our fermion because we want worldsheet supersymmetry. We can't get away with just using X's. We got to do fermions, but now if you do fermions, you have to obey all the manipulations of fermions, and that means Dirac type of Lagrangian, but it means Dirac type of Lagrangian on a curved manifold. So there's a lot of stuff to do, but you can get here. And even this turns out not to be right. Why not? Well, in Dr. Z's lecture, as well as in Robert DeMillo-Koch, we learned that when things are gauge invariant, if there's a gauge invariant present, then where you think ordinary derivatives occur, a gauge covariant derivative must occur. Now, in this theory, it turns out there's one more symmetry that we didn't take into account. And what is this symmetry? We can choose to locally rotate the two-dimensional spinor indices. That's a symmetry. It's certainly a global symmetry expression. And in fact, in general relativity, it must be a local symmetry of the expression. So this thing doesn't possess that symmetry. And again, if you remember Dr. Z's lecture, if you have a Lagrangian that doesn't possess the symmetry that you want, it's always the same prescription for doing that. You replace where an ordinary derivative is by a covariant derivative. I guess they didn't like covariant derivatives. So our final step is, here is an ordinary bare derivative. It doesn't respect the gauge symmetry associated with rotating this index. So according to the laws of gauge theory, you got to change this. So the final step to get the right answer, so correcting for local SO11 symmetry, because that's what it means to rotate a spinor index. It turns out that's SO11 symmetry. In order to do that, we take for the final form of the fermionic Lagrangian, I times the determinant of EAI times psi alpha mu times C mu delta times gamma I delta beta times EI A, and then in place of the ordinary derivative, you put a covariant derivative. I'm going to write that in the form of D's with two lines and an A acting on psi beta nu. And now this is well defined as soon as I tell you what that derivative is. D A. Well, does anyone want to contribute the first term to this derivative? How do covariant derivatives always look? What's the usual form? What's the first term? It's got to be a partial derivative. Covariant derivatives always start off with partial derivatives. So the first term here is dA. And now, from Dr. Z's lecture, you ought to be able to predict what else occurs. You have to add to this a gauge field, a connection. It's a quantity that we call, typically in the literature, it's called omega, and I'll give it a name in a moment, but it's typically denoted by the symbol omega. And then the only other thing that in order to get this completely correct, you have to insert one more matrix here. In fact, let me write this thing explicitly, because the explicit form of this object is that when it acts on this object, I'm sorry, there's a better way to write it. Let me write the derivative out. That's the best way to write it. We say that dA acting on psi beta nu is actually dA on psi beta nu plus omega A times gamma 3, well, I've got to define this object. I haven't done that so far, but I will shortly, times psi delta nu. That's the covariant derivative with respect to SO13. Now, what's this thing gamma 3? Gamma 3, well, because we went to 2 dimensions, there was already a gamma 1 times a gamma 2. Right? In fact, they're still on the board over there. Here's the two-dimensional gamma 0, and the two-dimensional gamma 1. So the way that we define this object gamma 3 is through their product. It's simply gamma 0 times gamma 1. That's its definition. And now, with this term and this term, we have achieved the construction of the what's called the spinning string. The spinning string is just the sum of these two theories. Now, remember, our whole reason for doing this is because we wanted somehow to get this notion of supersymmetry. And if you actually stop and think for a moment, you'll realize immediately that what I've written, in fact, cannot possibly be supersymmetric. Why not? Well, in our toy example yesterday, we had an x and a psi. That was yesterday's discussion. And in order for supersymmetry to occur, you needed both. So today we're talking about the string. There's an x, but now, yesterday our functions only depended on one variable, time. And same here. Today we're talking about functions that depend on two variables, and there are 26 copies of them. Supersymmetry says, well, if you start with bosons like that, you need the fermions, so that's how we got to the NSR fermion. So we say, well, we need an object that looks like this, and now there is the possibility of supersymmetry. I haven't proven it's there, but at least there's the possibility now, because supersymmetry says you need bosons and fermions. If you look at this action that I just wrote for you, namely this and this, yes, there could be supersymmetry between the x's and the psi's, but in each of these objects, there's one more function present. What's that function? It's E. E is a function after all, right? It depends on sigma and tau. It's another function. And yet what supersymmetry teaches us is if you have one function in a theory, supersymmetry says there must be an accompanying fermion. You can never have supersymmetry with just bosons. You also can never have supersymmetry with just fermions. So just as we have to introduce this thing, by the way, this kind of a combination is called a supermultiplet. So the collection of both that you need for supersymmetry is a supermultiplet. And now, interestingly enough for us, we have this other function. Here it is. And it's only a single function. You can't have supersymmetry like that. It's just not possible. So, there's something that's missing still. Even though we've worked very hard and we've made sure that X and psi have a supersymmetry and we've ensured coordinate invariance on the two-dimensional manifold, we still, in fact, don't have supersymmetry because the function E, which... Oh, I'm sorry, I missed Dr. Becker's lecture. Did she introduce the two-metric G in her discussion, yes? Okay, so you know that it's got to be there. And so the E is just sort of the square root of that function. And so we've introduced it, and yet for supersymmetry, it's unpaired. There's no fermion to accompany it. So we got one final problem. And the final problem that we have is that we must introduce a fermion that accompanies this function also. Now, this leads you to a theory called supergravity. And that's a theory. It's a complicated theory. However, we're going to write it down. It turns out it's not going to be too hard for us to write down. Yes, sir?
Sorry, before you go any further, you mentioned you were going to introduce an alpha omega A.
Oh, thank you. Thank you. Jock reminded me of something. I wrote the variable omega A, and at this stage, having introduced it, you may think it's an independent function. And that's exactly right. As I've done it, it is an independent function. But if you've studied general relativity, you should stop and think for a moment. In general relativity, there is something called the connection, and there's something called the metric. But in general relativity, you relate these two objects. So we here want to do the same kind of thing. We want to find a relationship between this object and the E's. And it's possible to do. How does it work? So we have to specify omega. I have to give you a determination of omega. Let me take my E object and saturate it with the sigma and tau derivatives. I get an object that's left over that is some kind of a derivative because it depends on derivatives. Things that are proportional derivatives are themselves derivatives also. So here's some kind of an object that's a derivative. Now the trick is rather interesting. Although this thing is a derivative times a function, the first thing you do is imagine that this is the generator of a Lie group, just as you've seen in Dr. DeMello Koch's lectures. If this thing were the generator of a Lie group, then one of the most important properties that it has are its structure constants. Right? So the first thing that we do is we we forget that it's really a function and depends on derivatives. We can imagine that it is a Lie algebra generator, and we calculate its structure constants. And from Robert's lectures, you know that structure constants come out of a calculation like this. Now, if these were really Lie group generators, on the other side of this equation, you must find the objects that you started with. You must find another. In the case of Lie groups, it's Tij equals some constant times Tk. If these things are treated exactly like Lie group generators, then you expect Ek to occur on the other side. And Ek is, again, another object like this, except that the K index shows up there in front, and where the I index is here. And now, of course, you need the thing that actually plays the role of the structure constant. So you must introduce a set of constants of proportionality here. So we're going to do that, Ijk. Now, the thing that's bizarre about this construction is this is easily doable. If you give me any function, any set of functions and multiply by the derivatives, I can actually make this calculation and figure out the value of this thing. But the interesting point is it's not a constant. It's a set of functions, but they are not constant functions. So Cij, K, actually have a name. They have lots of names, but one of the names is anhalonomy coefficients. These are the anhalonomy coefficients. Now, the anhalonomy coefficients, like I said, the definition is that you sort of close your eyes and hold your nose and treat the E's like a gauge, like a set of Lie algebra generators. That's how you define the anhalonomy coefficients. But once you have them, it turns out they're incredibly useful. Because, now to get back to Jacques' point, Jacques challenged me to define omega A. That was what his challenge was. Define this quantity. I have now a way to do so. It goes as follows. It looks very peculiar, but it works. I say, well, 0 is equal to E AI E Bj C IJK E K C. First of all, I'll just write this. You look at me and say, well, why in the world do you write that? Well, you have to go to the end of the story to figure it out. I'm going to start by saying 0 is equal to this. Well, that clearly can't be right because that demands actually that the C's are 0. And if you're doing C equals 0, it turns out you're not doing gravity at all. You're talking about flat space. So I'm going to add to this plus omega A, exactly the thing Jacques wanted me to define, times a factor of epsilon BC minus omega B epsilon AC. And what's epsilon? It's exactly the Levi-Civita tensor that you saw occurring in Robert's lecture, but for 2 dimensions now, not for d dimensions. It's the Levi-Civita tensor. So I put this as a condition. I say, I'm going to demand that the quantity omega is related to the quantity C through this equation. I just demand it. Now, this is an algebraic equation. And it turns out that not only is it an algebraic equation, but it's an algebraic equation that even I can solve. Let me do it for you. The first thing I notice is that this C index, the first thing I notice is that, first of all, this is a little bit messy for me, so I'm going to make my life simpler. And the way I'm going to make it simpler is multiplying by the inverse of this times the inverse of that times the inverse of that. Remember, these things are matrices. They each have an inverse. So I'm going to do that first. That's going to leave Cijk plus omega I times epsilon jk minus omega j times epsilon ik. If you just go through the arithmetic and doing the inverse multiplication, you'll see this is what comes out. So first, as I said, remember the steps are, take the matrix and multiply the inverse of that, and apply it to the entire equation. You get this. Now, once I have the equation written in this form, I remember that there's this flat Minkowski metric which carries indices ij and k, or I and j, and the flat Minkowski metric lets me raise and lower indices like this. So with the flat Minkowski metric, I'm allowed to lower this index. So I do so here. Let me write it here. Let me write the steps if you're taking notes. So the first step is use inverse, eliminate extra frames by appropriate multiplication. So we eliminated extra frames by appropriate multiplication. The next step is after we've eliminated the frames by appropriate multiplication, we then use the Flat-Minkowski metric to lower the k index. I jk plus omega I epsilon jk minus omega j epsilon ik. So that's true. The next step is rewrite this equation 2 more times, changing the indices, the order of the indices appear in a cyclic manner. So here at this stage, we lowered index using eta. And in fact, let me put the indices so we know what eta. We didn't use eta mu nu, we used eta ik or ij. So now I write these equations twice more, cyclically permuting the indices, and I'm going to write them all right up, one up under the other so you can see it. So it's Cijk plus omega I jk minus omega j epsilon ik. And now cyclic permuted means that you take the I index and push it to the rear consistently. So 0 is equal to C jki plus omega j epsilon ki minus omega k epsilon ji. That's one permutation. Then I do it once again. So 0 is equal to C kij plus omega k times epsilon ij minus omega I epsilon jk. So if the first thing is 0, these others have to be 0. The next step is you say, I'm going to take the first equation and put a plus sign next to it. I'm going to, I'm sorry, just a moment. There's something peculiar about this last equation here. And the peculiar thing is I didn't write the indices correctly. This should read ikj. You have to be very careful to cyclically permute the indices. Okay. So I'm going to take the first equation and put a plus sign next to it. I'm going to take the last equation and multiply the entire equation by also by a plus sign. And I'm going to take the middle equation and multiply every single term by a minus sign. And then I say, add the equations up. So first times plus, second times minus, third times plus, then add the results. Since I started with a 0 on that side, that part's really easy to add. On the other side of the equation, let's look inside of here and see how this works. There's going to be one term from this equation that says omega I epsilon jk. That term is going to be added to this equation, which reads omega I epsilon kj, but with a minus sign. But the Levi-Civita tensor, if you change the sign, order changes sign. So when I add this term to that term, they add together with a factor of 2. Everybody see that? So one term, let me write the C's first. There's a C, I, J, K, subtract C, J, K, I, plus C, K, I, J. I'm very afraid of that man, you know. So that's doing these parts according to the sign convention I set there. And now let's look at the omega piece. I have argued that these two factors occur with a factor of 2. Precisely because of using the property of Levi-Civita. So I get plus 2 omega I epsilon jk. So that takes care of this term and that term. What about all the rest of the omega terms? Well, let's start with this term, which has a minus sign here, and this term, because they're both proportional to omega j's. This one, however, I have multiplied by a minus sign. In fact, maybe it's best if I write it all out so you can see it. So I have a minus omega j epsilon ik from here, and I have a minus omega j epsilon ki there. And then I have one more such term, so now I've written this term and this term. I'm going to get these k terms here next. And if we look at them, we see that it's plus omega k epsilon ji, that's that term, And then also a plus, because of the way that we multiplied, plus omega k epsilon ij. So this is what I get from the arithmetic. But if you look very carefully, you'll see that, well, both of these have an omega j. They both have a minus sign. So I can factor that out and leave that as a plus. In a similar manner, there's an omega k here. They both have plus signs. I can pull this out and write it like that. But those are Levi-Civita tensors. And therefore, each of these two terms cancels, leaving me with one factor of omega that I can solve in terms of this. Now, for those of you who've had a course in general relativity, this process is very familiar because this is the way that you eliminate it's also the same procedure for eliminating the affine connection in terms of the metric. It's the same process, but these are not the same variables. So the solution that we find here is simply that omega I is equal to minus 1/2, because I'm moving all the c terms to the other side of the equation, dividing by 2, and then an epsilon j k, which would then make this into a 4, and then c ijk minus c jki, that's a plus ck ij. So that's the answer. I now have an expression for omega in terms of, it's actually in terms of E and its derivatives, because when you did the C calculation, there were derivatives inside of the definition of C. Okay, so now we go back to our string action, or at least our almost string action, because we had the bosonic term up here, we now have the fermionic term, but now we have completely defined this covariant derivative in terms of omega, and omega is now defined in terms of E and its derivatives. So do we have supersymmetry yet? I sure hope you would say no. No supersymmetry yet. Why not? Because for all the manipulations that I did, I never introduced a partner to E. The E field was still a single function, and supersymmetry says functions come in pairs. So I'm stuck. I still have my friend here, EAI, and he has no superpartner. He or she has no superpartner. But supersymmetry says you got to have superpartners, or else you can't have supersymmetry. So how do you get out of this? Well, let me, instead of working with this field, let me work with the other one that we introduced, namely EIA. It's possible to introduce a superpartner to this thing. By the way, for those of you who know about LIGO, this thing can be called, although we call it a Zweibein here, in the four-dimensional world we would call this thing a graviton. It is the gauge field for gravity. Now, so we still need this missing superpartner. So what to do? Well, just as we do before, you just toss one in. So we're going to introduce a superpartner. We're going to call it lambda. It's going to carry the same index as the E does down here, but it's supposed to be a fermion. And we don't, and if it's going to be a fermion, we have to really think carefully about indices now. It means, in particular, it must carry an alpha in place of this A, otherwise it's not a fermion. Alphas tell us that things are fermions. So the Zweibein, or two-dimensional or 2D graviton, has a superpartner, and the superpartner is what we call the gravitino. It's this thing. Now, we still, in the exercise yesterday, I showed you that you have to sort of add boson actions to fermions to get invariant actions. Here, if we add those two actions there, it turns out you still don't get a superinvariant. But but we're lucky because you're only missing one term. If we add, it's like in our toy example yesterday. I don't know how many of you actually went home and tried the homework, but in order to get a superinvariant, I started with both x and psi, but at some stage I introduced this thing f, and then in order to get the superinvariant, I had to take the f square contribution and add it to what looked like the standard terms. I try a similar philosophy here. I say to myself, well, if this superpartner exists, suppose it does exist, can I use it to write an extra term in the Lagrangian? That's the philosophy. Can we use it to write an extra term in the Lagrangian? The answer turns out to be yes. What kind of an extra term? Well, I'll call this coupling. I'll call it gravitino coupling. It turns out that, first of all, general coordinates invariance says we have to introduce our friend, that this determinant factor has got to be universal when you start writing these actions. So you have to write one here. So we have to do that. Let me take a term that is linear in our NSR fermion, so alpha and mu. I'm sorry, that's mine. And let me take something also linear in our bosons, so EIADA times x nu. And now we look at this thing. Thank you. We look at this thing, and we say, well, gee, it's not a scalar, so how do we make it a scalar? Well, there's an eta mu nu that needs to be contracted away, so we do that. That gets rid of that. I also said I was going to use this thing. Notice that this by itself cannot be a Lagrangian for a very simple reason. It's fermionic in nature. It's linear in fermions, and no Lagrangian can be linear in fermions. You have to have bilinears in fermions. So, therefore, I must introduce this object, so I'm going to. So lambda k, and it also carries an index. Let me put a beta there. It's still not a scalar, however. I've contracted away every single index except for these two. So now I've got to get rid of those two. I can do that by inserting in here a factor that looks like gamma I, gamma k times beta times alpha. If I insert that now, the thing's a complete scalar. And it turns out now, finally, after all of this work, so let me put a star here also. If I take the bosonic string action that you've been discussing with Melanie, add to that the fermionic action that we got motivated by saying it should look like Dirac's theory and use all kinds of symmetries, and then finally add to that the gravitino coupling term, the sum of those three things is the NSR string Lagrangian. That's how you get the NSR string. So it builds on the bosonic string, but it uses supersymmetry in two ways. It used supersymmetry to give us the superpartner to the string, and it used supersymmetry to give us the superpartner to the 2D metric that was always present in the bosonic string. You have to do both of them. Now, this theory I've defined, how much time do I have? What time? There's the clock. Now, is this lecture running an hour and a half? 3. Okay. 5 minutes or 2. The theory that we described, that we've now succeeded in describing, the theory that we've described so L spinning string equals L boson plus L fermion plus L gravitino coupling. This theory can be quantized by precisely the same methods that Melanie has taught you about. You can, first of all, go to the unitary gauge or the light cone gauge. I assume she discussed the light cone gauge, where you switch from D string coordinates to D minus 2 string coordinates. You can do that here. Works absolutely. When you do that, the net effect of that is that gets rid of the factors of E. Effectively, they sort of go away. But the numbers of size go away too. In that resulting theory, as it's consistently done, you can ask about the critical dimension. I assume Melanie told you that for the bosonic string, the critical dimension is D equal 26. If you repeat precisely those calculations for this theory, you find out D is equal to 10. So those extra 25 dimensions that you probably hated, well, there are less of them now. There are only 6 extra dimensions in this theory that you have to worry about. And it comes about precisely because we put supersymmetry on the world sheet. In the bosonic string lecture, you heard about the tachyon, no doubt. That the bosonic string has a particle whose mass square is negative. That object is not present in this theory. So the NSR string is a quantitative improvement over the bosonic string. It fixes a fair number of the problems that were present in the bosonic string. Yes, sir?
Are ghosts also eradicated by this?
Say again?
Ghosts, the ghost state.
Well, that was yes. I'm sorry. Yes, the ghosts are also absent. So it's a vast improvement. Critical dimensions improve. And in fact, this is sort of the modern beginning of talking about superstring theory. Now, this theory is not superstring theory. It's close. This is the spinning string. Now, why isn't it the superstring? You know, you'll remember I talked about string theories having 2 spaces associated with them, the world sheet and the target space. Now, the target space is an independent mathematical construct. It's a space just as good as any other space. So in the target space, you can ask yourself a question. Is it possible to introduce bosons and fermions that are only associated with the target space? The answer turns out to be yes. Yes, you can. And if you carefully study the Hilbert space, so you do quantization of this and look at the Hilbert space of this theory, that Hilbert space contains both fermions and bosons of the target space. So that's how we get target space spinors. It's a very non-trivial process. They come from the Hilbert space of this theory. However, if you do a simple counting, you'll find out that the number of bosonic states in the target space and the number of fermionic states in the target space are not the same number. Supersymmetry always says you got to have same numbers. And so in order to get all the way to the superstring, you take this theory, this is so-called NSR spinning string, Neveu, Schwartz, and Ramon. So this is their theory. In order to get all the way to the superstring, super is equal to NSR plus a projection condition. Projection on Hilbert space. You have to impose a projection condition on the Hilbert space. And what is this projection condition? You demand that the numbers of bosons and fermions be equal. Then you have the superstring. And I'm done.
Questions? Although I think most of them will take in the break.
Yes.
There's a question over there.
Yes.
Does that Lagrangian for the spinning string then describe both fermions and bosons?
Yes. It contains a description of both the space-time fermions and, the target space fermions and the target space bosons. They're both there.
Whereas after you introduced the spinners to the bosonic string, you got LF, and that describes the fermions.
I'm sorry, I got...
And then we added the spinners to that.
Right.
The use of frames.
Right.
To LF, is that what describes fermions?
In order to figure out what's being described, you have to follow things there. Well, what you do is you go to the string coordinates, and you expand it in harmonic oscillators. Expand the string coordinates in harmonic oscillators, and then it turns out that this thing. So, yes, it's oscillators from those. Those are also fermions in the theory. So all the fermions...
So if I understand it correctly, we could have combined some of the steps by simply